In category theory, a branch of mathematics, a natural transformation provides a way of transforming one functor into another while respecting the internal structure of the categories involved. Hence, a natural transformation can be considered to be a morphism of functors. Indeed, this intuition can be formalized to define so-called functor categories. Natural transformations are, after categories and functors, one of the most fundamental notions of category theory and consequently appear in the majority of its applications. Definition: if f and g are functors between the categories C and D, then a natural transformation eta from f to g is a family of morphisms that satisfy two requirements. The natural transformation must associate to every object x in C a morphism eta x, fg between objects of D. The morphism eta x is called the component of eta at x. Components must be such that for every morphism f, x, y and C we have. The last equation can conveniently be expressed by the commutative diagram if both f and g are contravariant. The horizontal arrows in this diagram are reversed. If eta is a natural transformation from f to g, we also write eta, fg or eta, fg. This is also expressed by saying the family of morphisms eta x, fg is natural in X. If, for every object x in C, the morphism eta x is an isomorphism in D, then eta is said to be a natural isomorphism. Two functors f and g are called naturally isomorphic or simply isomorphic if there exists a natural isomorphism from f to g. An infranatural transformation eta from f to g is simply a family of morphisms eta x, fg. Thus a natural transformation is an infranatural transformation for which eta yf equals g eta x for every morphism f, x, y. The naturalizer of eta, nat, is the largest subcategory of C containing all the objects of C on which eta restricts to a natural transformation. Examples: opposite group statements such as, every group is naturally isomorphic to its opposite group, abound in modern mathematics. We will now give the precise meaning of this statement as well as its proof. Consider the category GRP of all groups with group homomorphisms as morphisms. If is a group, we define its opposite group as follows. GOP is the same set as G, and the operation DOP is defined by ROP B equals BA. All multiplications in GOP are thus turned around. Forming the opposite group becomes a functor from GRP to GRP if we define FOP equals F for any group homomorphism F, GH. Note that FOP is indeed a group homomorphism from GOP to HOP. FOP equals F equals FF equals FOP HOP FOP. The content of the above statement is the identity functor i.e.the GRP. GRP is naturally isomorphic to the opposite functor OP. GRP. To prove this, we need to provide isomorphisms A to G, GGOP for every group G, such that the above diagram commutes. Set A to G equals A minus 1. The formulas minus 1 equals B minus 1 and minus 1 and minus 1 equals A show that A to G is a group homomorphism with inverse A to GOP. To prove the naturality, we start with a group homomorphism F, GH and show A to HF equals FOP A to G, i.e., minus 1 equals FOP for all A in G. This is true since FOP equals F and every group homomorphism has the property, minus 1 equals F. Double dual of a vector space if K is a field. Then for every vector space V over K we have a natural, injective linear map V asterisk from the vector space into its double dual. These maps are natural in the following sense. The double dual operation is a functor, and the maps are the components of a natural transformation from the identity functor to the double dual functor. Tensor homojunction. Consider the category AB of abelian groups and group homomorphisms. For all abelian groups X, Y and Z we have a group isomorphism hom. These isomorphisms are natural, in the sense that they define a natural transformation between the two involved functors AB times ABOP times ABOP AB. This is formally the tensor homojunction, and is an archetypal example of a pair of adjoint functors. Natural transformations arise frequently in conjunction with adjoint functors, and indeed, adjoint functors are defined by a certain natural isomorphism. Additionally, every pair of adjoint functors comes equipped with two natural transformations called the unit and counite. Unnatural isomorphism. The notion of a natural transformation is categorical, and states that a particular map between functors can be done consistently over an entire category. Informally, a particular map between individual objects is referred to as a natural isomorphism, meaning implicitly that it is actually defined on the entire category, and defines a natural transformation of functors. Formalizing this intuition was a motivating factor in the development of category theory. Conversely, a particular map between particular objects may be called an unnatural isomorphism if the map cannot be extended to a natural transformation on the entire category. Given an object X, a functor G, and an isomorphism, proof of unnaturality is most easily shown by giving an automorphism that does not commute with this isomorphism. More strongly, if one wishes to prove that X and G are not naturally isomorphic, without reference to a particular isomorphism, this requires showing that for any isomorphism eta, there is some A with which it does not commute. In some cases a single automorphism A works for all candidate isomorphisms eta, while in other cases one must show how to construct of different A eta for each isomorphism. The maps of the category play a crucial role. Any infranatural transform is natural if the only maps are the identity map, for instance. This is similar to concepts in group theory or module theory, where a given decomposition of an object into a direct sum is not natural, or rather, not unique, as automorphisms exist that do not preserve the direct sum decomposition. See structure or theorem for finitely generated modules over a principle. Ideal domain uniqueness, for example. Some authors distinguish notationally, using for a natural isomorphism and for an unnatural isomorphism, reserving equals for equality. Example: fundamental group of torus is an example of the distinction between the functorial statement and individual objects. Consider homotopy groups of a product space, specifically the fundamental group of the torus. The homotopy groups of a product space are naturally the product of the homotopy groups of the components, with the isomorphism given by projection onto the two factors. Fundamentally, because maps into a product space are exactly products of maps into the components, this is a functorial statement. However, given the torus, which is abstractly a product of two circles, and thus has fundamental group isomorphic to Z2, but the splitting is not natural. Note the use of and. This abstract isomorphism with the product is not natural, as some isomorphisms of T do not preserve the product. The self-homeomorphism of T given by acts as this matrix on Z2 of invertible integer matrices, which does not preserve the decomposition as a product because it is not diagonal. However, if one is given the torus as a product, equivalently, given a decomposition of the space, then the splitting of the group follows from the general statement earlier. In categorical terms, the relevant category is maps of product spaces, namely a pair of maps between the respective components. Naturality is a categorical notion, and requires being very precise about exactly what data is given. The torus as a space that happens to be a product is different from the torus presented as a product. Example: dual of a finite-dimensional vector space. Every finite-dimensional vector space is isomorphic to its dual space, but there may be many different isomorphisms between the two spaces. There is in general no natural isomorphism between a finite-dimensional vector space and its dual space. However, related categories do have a natural isomorphism, as described below. The dual space of a finite-dimensional vector space is again a finite-dimensional vector space of the same dimension, and these are thus isomorphic. Since dimension is the only invariant of finite-dimensional vector spaces over a given field, however, in the absence of additional constraints, the map from a space to its dual is not unique, and thus such an isomorphism requires a choice, and is not natural. On the category of finite-dimensional vector spaces in linear maps, one can define an infranatural isomorphism from vector spaces to their dual by choosing an isomorphism for each space. But this will not define a natural transformation. Intuitively, this is because it required a choice, rigorously because any such choice of isomorphisms will not commute with, say, the zero map. See for detailed discussion. Starting from finite-dimensional vector spaces and the identity and dual functors, one can define a natural isomorphism, but this requires first adding additional structure, then restricting the maps from all linear maps to linear maps that respects this structure. Explicitly, for each vector space, require that it come with the data of an isomorphism to its dual. In other words, take as objects vector spaces with a non-degenerate bilinear form. This defines an infranatural isomorphism. One then restricts the maps to only those maps that commute with the isomorphisms, or in other words, preserve the bilinear form. The resulting category, with objects finite-dimensional vector spaces with a non-degenerate bilinear form, and maps linear transforms that respect the bilinear form, by construction has a natural isomorphism from the identity to the dual. Viewed in this light, this construction is completely general, and does not depend on any particular properties of vector spaces. In this category, the dual of a map between vector spaces can be identified as a transpose. Often for reasons of geometric interest, this is specialized to a subcategory, by requiring that the non-degenerate bilinear forms have additional properties, such as being symmetric, and positive definite, symmetric sesquilinear, skew-symmetric and totally isotropic, etc. In all these categories, a vector space is naturally identified with its dual, by the non-degenerate bilinear form. Operations with natural transformations. If eta, fg and epsilon, gh are natural transformations between functors f, g, h, c, d, then we can compose them to get a natural transformation epsilon eta, fh. This is done component-wise. X equals epsilon x eta x. This vertical composition of natural transformation is associative and has an identity, and allows one to consider the collection of all functors CD itself as a category. Natural transformations also have a horizontal composition. If eta, fg is a natural transformation between functors f, g, cd and epsilon, jk is a natural transformation between functors j, k, d, then the composition of functors allows a composition of natural transformations eta epsilon, jf kilogram. This operation is also associative with identity, and the identity coincides with that for vertical composition. The two operations are related by an identity which exchanges vertical composition with horizontal composition. If eta, fg is a natural transformation between functors f, g, c, d, and h, d is another functor, then we can form the natural transformation h eta, hfhg by defining if on the other hand k, bc is a functor, the natural transformation a to k, fkgk is defined by functor categories. If C is any category and I is a small category, we can form the functor category Ci having as objects all functors from I to C and as morphisms the natural transformations between those functors. This forms a category since for any functor f there is an identity natural transformation 1f, ff, and the composition of two natural transformations is again a natural transformation. The isomorphisms in Ci are precisely the natural isomorphisms. That is, a natural transformation eta, fg is a natural isomorphism if and only if there exists a natural transformation epsilon, gf such that eta epsilon equals 1g and epsilon eta equals 1f. The functor category Ci is especially useful if I arises from a directed graph. For instance, if I is the category of the directed graph, then Ci has as objects the morphisms of C, and a morphism between phi, u, v and psi. X, y and Ci is a pair of morphisms f, u, x and g, v, y and c such that the square commutes, i.e., psi f equals g phi. More generally, one can build the two-category cat whose zero cells are the small categories. 1 cells between two objects and are the functors from 2 cells between two 1 cells and are the natural transformations from 2. The horizontal and vertical compositions are the compositions between natural transformations described previously. A functor category is then simply a Hom category in this category. Untitled dilemma. If X is an object of a locally small category C, then the assignment YHOMC defines a covariant functor fx. C set. This functor is called representable. The natural transformations from a representable functor to an arbitrary functor f. C set are completely known and easy to describe. This is the content of the Untitled dilemma.